here understanding today. Really, again, just a few flashcards in your set. So what resting membrane potential is the difference in electrical charge between inside and outside of the cell at rest. So it is just what it sounds like. And the generic resting membrane potential we're going to use is minus 70. So minus 70 millivolts. So minus 70 millivolts from inside to outside. So the inside is a little bit more negative to the outside. People pretty much figured this out over 100 years ago. So you think, well, what did you have over 100 years ago? Did you have computers? No. Did you have... So it's really pretty amazing. So people were able to calculate the mass of the moon by rolling a little ball down a slope and seeing how much it deflected from the gravity to within like 1% of the actual mass that we could calculate now. So pretty amazing. People could really get at things. And what people knew was that there's a difference in the concentration of potassium when you measured inside of the cell versus outside. And what we mean by outside is not so much like the air here. It would be the extracellular space. So the space, say, in between neurons or in between muscle cells. So you had this difference in potassium concentration, and you have this charge across the cell. Now, there's also a difference in sodium concentration that's just about the inverse. Outside the cell, you have high sodium. Inside the cell, you have low sodium. Outside the cell, you have low potassium. Inside the cell, you have high potassium. So you have these differences in ions across the membrane. And actually, if you're just to look at them, they sort of balance out. So you have about 140 millimolar sodium outside the cell, balancing the potassium inside the cell. And vice versa, you have a lot of chloride outside of the cell, which is, of course, negative. But you have a lot of negatively charged things inside the cell, like amino acids and nucleic acids. So if you were just to consider the charged molecules at rest without them moving, they're not actually going to cause the resting membrane potential, this membrane potential across the membrane. So it can't be accounted for just by the differences in ions. So it has to be something else. And so Nernst, in an initial experiment, just looked at, well, what happens if you look at the movement of potassium chloride? So he set up two beakers and filled one with 1 molar potassium chloride and one with 100 millimolar potassium chloride, and put it, everyone knows what Whatman paper is. It's like that lab paper that is sort of absorbent, but sort of not, and just made a bridge. And because it's Whatman paper, osmosis is going to carry our potassium chloride solution across the bridge, and you know which direction it's going to move in. It's going to follow initially what? Yeah, it's going to follow the concentration gradient. So potassium and chloride are going to move across the bridge from high to low. But chloride, it turns out, is going to move a little faster than potassium. Why? It's smaller. Yeah, so it's going to move a little faster than potassium. And because it has a negative charge, it's going to set up a charge difference across these two beakers. And so what this demonstrated is that the movement of ions, so different movement of ions, was actually in itself sufficient to set up a potential. So you could read the voltage difference between these two beakers, and you would get a voltage difference because the ions are moving at different speeds and they have different charges. So now chloride's moving faster. You're going to establish a charge. And where is your negative charge going to be? This beaker or this beaker? Very few ions are actually moving, so we can just always consider this 1 molar or 100 millimolar. Are you going to have more negative charge in your 100 millimolar beaker or your 1 molar beaker? 100 millimolar, yeah, because there's a few more chlorides moving into it. And so now, what's that going to do? What's that going to do to the speed at which the ions move? Good, it's going to speed up potassium because the potassium has a positive charge, and it's going to repel the chloride a little bit. And eventually you're going to reach an equilibrium at which your movement is balanced. And I guess I've answered the question. So, what's this help? There. So you have that moving, and you're going to reach an equilibrium because of it. So what you can see is that some really simple natural homeostatic mechanism can set up a charge and can set up a balanced charge. So it's nice to have a charge difference across the membrane, but not if it becomes extreme. So you need some sort of way to balance that out. And this is what does that, so that increasing pull or repulsion depending on how the charge is built up. So now our next question is, well, that's great. Like, here's 2 beakers, and you're saying, this is how your brain works. You have 2 beakers and a piece of Wattman paper. And it seems crazy, but of course they were right. But let's actually look at a neuron. And in a neuron, what you'll have, if you compare the intercellular environment and the intracellular, sad story, exam a couple years ago. One student mixed up inter and intra on all of the questions. It was really, the student passed, but make sure you know, so inter is like between cells. Think of like international. It's like between nations. And intra is inside. I mix this up in my brain all the time. I'm going to say it wrong, and you're just going to stop me. Just stop and say, no, you got it wrong, and then I'll stop. But make sure on your exams that you remember it. So our membrane, it turns out, is a little bit more permeable to potassium than it is to sodium. And we can just, for now, just consider that potassium a little bit is leaking from inside the cell to outside the cell. And because these are positive ions, you're going to start to accumulate a positive charge. Where? Outside, good. And then inside the cell, you have this negative charge. So you have this negative charge lined up across on the inside of the membrane. And so these 3 questions are what we're going to cover in the second part of today's class. So why does it stop there? So why does resting membrane potential reach? -70s are generic point. This is a generic point. So in some cells, muscle cells, it might be -66. In some neurons, it might be -40. It's going to depend. We're just going to use -70. And then where are the ions? So that's what we need to consider here. And what we can do is use an equation that was developed to model this. And this is called the Nernst equation. So I mentioned this earlier. And what the Nernst equation does is it describes at equilibrium, at a steady state, what's happening. So you've developed this charge. And now what's that going to do to movement of potassium? Where is there a lot of potassium? Inside the cell. And where's your negative charge?
Inside the cell.
Inside the cell. So what's that going to do to movement of potassium?
Slow it down.
Slow it down, yeah, because the potassium, it likes that negative charge. I don't want to leave. I'm going to stay with this negative charge. So equation, here it is. It's the Nernst equation. E is the equilibrium potential. You might have learned this as the reversal potential. It's the charge at which movement of an ion will change direction. across the membrane. So we have the equilibrium potential of an ion. So ion X, we can put in whatever ion we want. And there's really 4 ions to keep track of: potassium, sodium, chloride, and calcium. We're going to cover potassium and sodium today. So the values in the Nernst equation, well, we've got our universal gas constant. So there it is, it's a number. We've got temperature, so Kelvin plus degrees in Celsius. So what's our temperature in Kelvin? Bust out your calculator, it's okay. Yeah, right around there. Throw in your 0.15 and you're set. So we've got our temperature. So we've got universal gas constant. We've got temperature in Kelvin. So you multiply those together. And then you divide them by the product of Z, which is the valence of the ion. So sodium and potassium, Z is +1. Calcium, Z is +2. Chloride, Z is -1. So Z and F is Faraday's constant. And because we're going to be talking about things in terms of millivolts, we can just lop off the zeros at the end and consider that to be 96.5. Now, what I want you to do is to calculate the equilibrium potential for potassium. So I want everyone to do this, and don't say the answer as soon as you get this. Our values here is potassium outside the cell versus potassium inside the cell. So this is the original Nernst equation. Because I'm lazy, I just rearrange it so I can get rid of this minus sign. So if you just flip over the out and in. So it's concentration outside over concentration inside of potassium. So 4 over 140. So those are the values we're working with. So 4 millimolar outside, 140 millimolar inside. And we take the natural log of it. Who remembers what the natural log is? That's a fun one. Like some arbitrary number, 2.8, and if you take it to this power, the natural log power, you get your value. No math majors? All right, so take 20 seconds or 30 seconds or a minute. The nice thing about this is you can do the equation piece at a time. So everyone see where the different numbers plug into the formula? So who has an answer? All right, sorry guys, we're gonna wait another. It's not enough. Who has an answer now? All right, I want 3 people to raise their hand and you have to give us your answer. Negative 95-ish, who else? John. All right. Anyone else? So some of your values are off a little bit, but you're doing it right. So it's just two decimal places off. So our value of the Nernst equation for potassium, the equilibrium potential for potassium is minus 95 millivolts. So that is amazingly from the simple formula, able to describe the movement of potassium across a membrane. So potassium movement 1 across a membrane will cause the membrane potential to reach minus 95 millivolts. That's one thing to keep in mind. 2, depending on which side of minus 95 you're on, that will dictate the direction that potassium moves. So if you're at minus 70 millivolts, where's potassium going to move? It's going to move out. What if you're at minus 110 millivolts? It's going to move in, actually, even at these values, because the electrical pull will be strong enough to overcome the chemical gradient. And we're going to see that when we talk about skeletal muscle physiology. So we'll talk about something called the reversal potential. But it's important to keep in mind that these equilibrium potentials are also true for the individual ions and individual membrane. So movement of potassium, that is sufficient to cause your resting membrane potential to reach minus 95 millivolts. At minus 95 millivolts, the amount of potassium moving out will equal the amount of potassium moving in, and you reach that point. What did I say resting membrane potential? 70. Negative 70, all right. So there's something going on. Should we do more calculation? Let's just do one more. So I want you to calculate. You can calculate these on your own. So maybe tonight go over those. So just to give you some practice with working with the Nernst equation, there's this really great online calculator that we'll use a little bit more when we talk about action potentials. You have to sort of ignore the permeability setting, but if you put in the ion concentrations, you'll see that you'll get different values there. Use your calculator. There's going to be a ton of online calculators just as a practice. But what I want you to do is calculate the equilibrium potential for potassium for our patient with hyperkalemia. So this was our patient with nephritis. So the kidneys aren't working as well. They're not really secreting potassium. Your serum ion balance is off. And so now you have 7 equivalent millimolar outside versus 140 in. So go ahead and now calculate the equilibrium potential for potassium with those values. You'll do this in the clinic all the time. Come on, you'll draw some serum, you'll measure it, you'll whip out your calculator. You'll calculate the nerd's potential and say, actually. Who's got it? Raise your hand. So if I make you write it down on a piece of paper, you'll all write it down, hand it in. Higher or lower?
Lower.
Lower. What did you get as a value?
-80.
-80, yeah, so pretty different, less negative. Yeah, that's a good point to keep in mind. So the equilibrium potential is different. And does that make sense why it is? Why would the equilibrium potential for sodium be that much different? 15 millivolts, that's a lot. You'll see that's 3 times what's needed to actually depolarize a neuron. 5 millivolts. 5 millivolts will depolarize it. So why is that? What's happening here? So let's ignore the charge for a second. What happens to the chemical gradient? Yeah, you have less of a chemical gradient. Does it seem like a big change? Why not? So our change in sodium, if you calculated our change in sodium, when you calculate it tonight, what you'll see is that there really isn't a big change in the resting membrane potential for sodium. But here you've changed by 10. Here you've only changed by 3. So why do you have a bigger effect with potassium than from sodium?
Outside concentration.
It almost doubles. Good. So if you were to express it as percent compared to normal, it would be huge, whereas the sodium change wouldn't be as dramatic. So when you're in a situation where a patient has hyperkalemia, or actually hypokalemia, you're going to change the resting membrane potential. And so keep that in mind with our patient as we get back. So back to the nerds. So resting membrane potential is actually around -1 or -70, whereas the potassium equilibrium potential is -95. So the initial investigators, they called it a day. They said, we've got it. It's potassium. You know, this is pretty close. That's just experimental error of the system. So, but they were off by quite a bit, if you think about it. This is 5 times the difference that would be needed to actually stimulate a neuron. These are my famous Humboldt squid. So years like this, when it's La Nina or El Nino, these will come in off the coast of the Pacific. So California, you can go out and catch Humboldt squid. And it turns out part of their result was because they were using the squid as a model organism. So squid, it turns out, is the original model organism for neuroscience. And the reason is that they have a squid giant axon. And they would find a large squid giant axon, not a giant squid large axon. This would be a large squid giant axon. So as we'll see, the diameter of the axon influences how quickly electrical signal can move down it. And the squid have evolved this huge axon to trigger their escape reflex. So it's about 1 millimeter in diameter. So if you're working 100 years ago, 110 years ago, well, this is a realistic model to actually study neurophysiology. The squid has different physiology, and so they, in doing this, they said, well, it's a little bit different, but let's just look at it. So they calculated the Nernst value for potassium concentration versus the equilibrium potential / resting membrane potential compared to the actual value. And so when you reach an equal potassium concentration, then you sort of level off. But before that, your curve is deflected. So what it indicates is that potassium can't really account for everything in this system. And if you were actually to calculate the equilibrium potential for squid based on their ionic composition, you'll get something closer actually to -70. But you can do that a little bit later. So what it turns out that is at the same time that some potassium is leaking out, some sodium is leaking in. And so you have sodium, which are positively charged, leaking in, and this somewhat counterbalances the potassium leaking out. And so you have more potassium leaking out, you have a little bit of sodium leaking in, and this balance sets the equilibrium potential of the membrane at about -70. So at resting membrane potential at -70, the sodium influx is equal to the sodium efflux. Same with potassium. The number of ions are balanced, and the water is also balanced. So at -70, you reach a steady state. Some cells, it's going to be a little different. Again, I'm using -70 just as a generic number. Different tissues will be a little bit different. And this is regulated just homeostatically, so just the movement of the ions.
So their error was kind of twofold. A, their animal model, obviously. And the second was that they thought the rest of memory only relied on the flux.
Yes.
And they didn't take into account any other.
Yes. Yep. And it's nice to know, but that's it.
I was just trying to make sure.
It won't. It absolutely won't be on your exam. So again, you have both sodium and potassium moving. I might have hit up instead of down there, or duplicated the slide. And what I just mentioned is that actual resting membrane potential is going to differ in different cells, in different tissues. So these are the concentrations of potassium inside and outside your cell. And this is the equilibrium potential that if you use this value to calculate that you would reach. So equilibrium potential of sodium for these different tissues. And here's the actual resting membrane potential of those tissues. So the next slide has a question that's going to be, which of these is the least or most likely to sodium? Let's just hit it here. Which is the least leaky to sodium? And how do you know? The glial cells. Why? How do you know that? Yeah, because the resting membrane potential is essentially set by the equilibrium potential for sodium. What cell type is most leaky to sodium? Sure.
Animal nerve.
It's most likely potassium.
So the equilibrium potential for sodium is what it would be if you only had, or potassium, I'm sorry. This would be if you only had potassium in movement. and this is reality. So what is the most leaky? Good, the mammalian nerve. So not the squid axon, because that's really not a big difference there. And it's different just because seawater versus inside a squid is different than us by a little bit. So when you're going through, you can review that just for that concept. We'll see this in different systems, that the resting membrane potential will be a little different. So I think muscle, we use minus 65 or minus 66 as a baseline. So what we could summarize here, so all of this in your brain, apart from the Nernst equation and how you would calculate that, is that resting membrane potential what? Who can summarize with one sentence? One sentence, the most concise, descriptive sentence. All of your classmates will be like, thank you. Resting membrane potential. What is it? It's the, you know the name, so the name describes what it is. No. We're done with homeostasis. Part one, okay, so we're gonna have a long sentence. It's gonna be a compound sentence.
Is it something along the lines of the sodium potassium movement across the chemical gradient in itself establishes an electrical gradient which sets up?
That would be
convoluted.
that would be a sentence. So you have every piece there. You have every piece you need there. So resting membrane potential.
What's the voltage difference at equilibrium?
At equilibrium, and then we need to have, which is set up by sodium and potassium leakage. That's next. That's how we get there. Potassium leaking out, sodium leaking in. Good. So that's it. The class itself is really simple. And so just the key is to go through and summarize everything down to a few points, and then you've got it. So neurophysiology, it's not some difficult course. It's actually really simple. And just put in the time and summarize this. What Nick alluded to was, how is the gradient established in the first place? So we know now that the gradient is established by something called the sodium-potassium ATPase pump. So this is a pump that cleaves ATP, and it pumps some sodium and some potassium, both against their gradient. And so initial experiments, we're just looking at salt. Here's a squid axon, and we put it in cold water. This was probably experimental error. There was probably some grad student who was like, yeah, I'm going to go to lunch. Like, I'll just put my squid axons on ice. And then, came back and, like, the squid axons are all swollen. And it's like, oh, no, like, I have to go catch more squid or whatever you have to do this. And so, so then they put the squid axons back in warm water, and they returned to size, and they probably just continued their experiment and didn't tell the head of the lab, at least in my imagination. So this is because, all right, we've got a pump, and it's a biological system, and so the pump's activity slows down. The pump's activity slows down, and so salt's going to accumulate inside of the axon, and then water will follow and swell it up. So we've got a pump. It's a biological pump, and we can demonstrate that by temperature. So its activity goes down. So resting membrane potential, we have to understand sodium movement a little bit. Sodium movement's going to be important for our action potential. So now, all right, the grad student is like, like I did this system and I can take long lunches. And the PI finds out, it's like, no, we're going to make you fill squid axons with radioactive sodium. And look what happened. So poor graduate student fills the squid axon with radioactive sodium and now has to look at movement of sodium out of the axon. So what we're looking at is just over time, this radio-labeled sodium is going to leak out of the axon, and we're just going to measure that. So this is sodium efflux. So sodium being pumped out of the cell. So if your pump is active, then you have this radioactive sodium being pumped out and mixing with all of the other normal sodium that you're bathing it into. And over time, you see this efflux, and it goes down because eventually you pump out the radioactive sodium. And that's our experimental system. So the first experiment was just to try this with potassium-free solution. So you try no potassium. Well, now all of a sudden the sodium stops getting pumped out. So what did this tell us?
It's combined with a potassium pump.
Yeah, so it's a sodium-potassium pump. So now we're going to bathe it in a chemical called DNP. And you'll notice with some of your slides, there's little subnotes hidden down here that will sometimes explain the abbreviations, not because you need to know them, but just to save you from doing a Wikipedia search or something like that. So DNP is going to inhibit ATP synthesis. And so now you have ATP plateauing. So what does this tell us? Yeah, so it's a sodium, potassium, ATPase. So really a pretty advanced conclusion that was made with really pretty basic experimentation. And then cold water back into warm water. So this is the original accidental experiment. And this is all just in my head, like it's something I made up. I don't actually know if that's what happened. It's just how I imagine it working. So you put it together, so you have a sodium, potassium, ATPase. It's metabolic, and so you're concluding that you're using ATP to exchange sodium and potassium. Where are you pumping sodium from? Out of the cell, yeah, so you're pumping sodium from in the cell to out of the cell. And what about potassium? Opposite. And maybe you learned this in your earlier class. What's the ratio?
3 to 2.
3 to 2. Which is 3?
Sodium.
And which is 2?
Potassium.
All right. And what can this account for? Why would you want this ratio? There's 2 reasons, really. What's that? You want to set up the charge gradient, but why would you pump? I mean, that's sort of a 3 to 2 ratio is a pretty big difference. What do you know about the difference in how potassium moves versus sodium?
Sodium's leaking.
Which is leaking faster?
Potassium.
Potassium. So that doesn't really make sense,
Is
does
there
it?
more sodium in the body?
More sodium? So it's a trick question. It's to see if you read ahead. Sodium's actually used, the sodium gradient's used as an energy source for the antiport and synport. And one of the very important clinically relevant pumps is the sodium-calcium antiport pump. So if you have a sodium-calcium antiport pump, I should tell you, calcium is very, very low in the cytosol of the cell, just tiny amounts. And it's at tiny amounts because calcium regulates a lot of different biological. And you need to either pump it into the smooth ER or the cell type specific equivalent like the sarcoplasmic reticulum, or you need to pump it outside of the cell where it's found in higher concentration. So I told you that it's a sodium-calcium antiport pump, and it's using the sodium gradient as its energy source. So which direction is sodium going to be moving? Inside to the cell. So that's our energy source, and then that's going to pump calcium where? Out of the cell. Good. This is actually, it turns out, indirectly our target of wobble, so our cardiac glycoside. So that is going to directly target the sodium-potassium ATPase pump, and because that's not as efficient, the next stage won't be as efficient, the sodium-calcium antiport pump. And we'll see in a minute how that all adds up with our patient. So I just mentioned that, so not in a minute, in like a second. So drugs like digitalis or its synthetic analog wobble are used as cardiac glycoside. And the way they work is that if wobble or digitalis are added, there's a small little blip, there's a small, like 1 millivolt depolarization, and then over time, you lose resting membrane potential. So for your neuron, you're going to fire somewhere, when you're depolarized about 5 millivolts, and you're going to keep being active. How can you use this to treat someone with congestive heart failure? So that's really what we want to address here. So I told you the sodium-potassium ATPase is the target of this. And so what's that going to do? And so just because of the way the sodium and potassium are balanced, you're going to tend to have a bigger effect on sodium inside of the cell. And so you have more sodium inside the cell, slightly more. So what's going to be less efficient? We just talked about it. Good. So you have less of a gradient with sodium outside and inside, and so your pump doesn't have as much energy. There's not as much energy in that sodium gradient anymore. So you're not going to be able to pump calcium out as much. Now calcium inside the cell can do all sorts of bad things. So it can cause neurotoxicity. If someone has lots of epilepsy, then it can cause the neurons to die because the calcium's active and it activates all these other things. But it actually is also important for muscle control. So if you have more calcium inside the cell, because you've secondarily inhibited its extrusion, the cardiac muscle is actually going to beat more forcibly. And so that's why you would use that as a medication to help someone whose heart isn't working as much as it could if you treat with something. Here is just a summary slide of ions and movement. This is more for your convenience. I think that I've said this throughout the course, so it's just a summary of where everything is. We are inside the cell, and these are just our generic values, so these aren't exact. They're going to be different a little bit in different systems, sometimes wildly different, as we'll see. A is just my abbreviation for anion. So you have a lot of negatively charged anions in the cell, like amino acids and nucleic acids that aren't permeable across the membrane. And those actually are balanced out by chloride. So your resting membrane potential is set up initially by the sodium-potassium ATPase pump, setting up these gradients of molecules. And we'll see that this pump actually, because it's pumping 3 to 2, it actually will have a small effect on resting membrane potential relative to the cardiac muscle that we'll talk about at the end of the semester. But for now, we can just consider it setting up these gradients, and the movement of ions across the membrane is going to set our resting membrane potential at our value of -70. Again, just some text to go with that, so when you're reviewing this, you can go over it. So we have our 2 case studies. We have our patient who had elevated serum potassium because of nephritis. So what neurological and cardiac complications might be expected. Where would you expect resting membrane potential to be? Well, we calculated the potassium equilibrium was about -80. And so resting membrane potential is -70, so that's still less polarized, but you still have movement of sodium. So take it a step further. Where will we be from -70? We'll be, yeah, good. So we'll be less polarized. And neurons, it turns out, can adapt to this somewhat. So neurons, they have a little more flexibility, but cardiac pacemakers aren't so good at that. So cardiac pacemakers won't really be able to adapt to that so well. And your patient would be at risk of developing arrhythmias. So potential arrhythmias because the cells are going to be a little bit depolarized in this condition. Now, if you surgeons, as we'll see tomorrow, are conducting heart surgery, you can actually use this as a trick to shut the heart down so that you can perform surgery without it beating on you, which would probably complicate. So again, your equilibrium potential for potassium is going to be at a relatively higher value, so -80. And that will set resting membrane potential a little bit higher as well. And what you have to worry about is cardiac pacemakers. So again, we'll get to that probably actually the last actual class period. Again, so we have another patient with congestive heart failure, and we've prescribed digitalis. And we reviewed the mechanism of digitalis and other cardiac glycosides. So this is something I expect you to know. It's relevant. They're very common drugs. What would happen with an overdose? We've inhibited the sodium-potassium ATPase.
Dangerous.
We're not worried about that. We've got some other problem. That eventually is going to be what happens. But why? What? So if you don't have that, so this is why you would use the drug. So you'd want higher strength of contraction with more calcium. But if you were to block the sodium-potassium ATPase pump too much, what do you start to lose? Polarization of your membrane. So you're going to lose your resting membrane potential is going to be less and less polarized. And like the hyperkalemia, that's going to cause problems with arrhythmia. So when you start to deviate too much from normal resting membrane potential, you're going to have first problems with arrhythmias, and of course eventually your nervous system will shut down or just become constantly active because you're going to have depolarization. As we'll see, you actually have to repolarize to reset neurons. We'll save that for Thursday. So again, just review so you have it there. So your cardiac muscles are going to be really vulnerable to elevated potassium. We'll see their physiology is actually quite different from the generic neurophysiology that we'll cover tomorrow. So this is also a case if you have hypokalemia, and you have hypokalemia if you're a supermodel or a famous actress, right? Because all of the bright light shines on you. And what's the connection here? What late at night was I thinking when I did hypokalemia Google search? Anorexia. Yeah, so not enough potassium. And again, resting membrane potential. We summarize this little mini section with a number of slides that shows what happens if you change ionic balance to resting membrane potential and so on, but that's a day or so from now. So not only would elevated potassium be dangerous, but so would low potassium. So they're both going to change resting membrane potential. And those both actually can influence heart rhythm, and so that's the main danger there. So OD, again, just to review, if you're giving Wabang, the idea is to paralyze the sodium-potassium ATPase pump a little bit to keep calcium inside the cell. But if your dose of digitalis or Wabang, your cardiac glycoside is too high, it's going to cause you to lose resting membrane. This is just an explanation of that. So when you go back to study, there it is. There's a little cartoon for you. So imagine in your imagination that I say to draw this somewhere. I don't know why I'd ever say that. Like in my twisted imagination, when I'm like, it's like 1 a.m. and I'm like, oh no, I have to write 40 more exam questions or something like that. This is the sort of thing that would pop into my mind. Say, all right, let's see how well they know this. And it's not tricky. It's just making sure you understand how you can change physiology a little bit to have a desired outcome. So again, our rationale, and I'm just kind of flying through this because it's the end of class and I want to let you all go. So this is what, you in an extreme case need to give this person a pacemaker and some sort of breathing control, respirator, because if you didn't have neural or cardiac function, that's not conducive to healthy life. It turns out that potassium, actually in this case, oddly, can help to counteract some of these overdose problems. So you could tell your patient, in some cases, especially hypokalemia, to eat a banana. Would you want your kidney patient to eat a banana? A whole bunch of bananas, right? If he has high potassium, what's higher potassium going to do? It's going to make it worse, yeah. And so you'd want to avoid that sort of thing. So something very simple like eating a banana or not eating a banana is really critical. So McDonald's had this advertising campaign a few years ago to convince people to eat French fries because they have as much potassium as a banana. It didn't work. So that's the connection. So really simple things. I wish we had more time to cover this. Maybe if we have a little more time. Have you ever heard of using electrical fields to heal wounds? So your cells, not only do they have electrical potential across them, but the basement membranes of your tissue actually have an electrical potential too. And when you make a wound in the basement membrane, say a puncture wound, it actually sets up an electrical potential there. And cells will be attracted to that electrical potential and will crawl in and heal the wound. And so people test electrical stimulation to try to increase migration. And where it's probably going to be useful is for diabetic lesions. So people with diabetes often develop lesions that don't heal well, and it's thought that electrical stimulation is a good thing to do. So there's a lot of clinical trials in that. And I'm glad I didn't plan on having you review everything and make little presentations because you'd riot now. But I think on Thursday we'll have a little bit more time and we can have a group activity so it's not just me being blah, blah, blah. So